Welcome to our webinar on agriculture R&D, a neglected crucial public good, brought to you by CIFER, the Council on Food, Agriculture and Resource Economic. My name is Gal Hachman, I'm the CIFER Board Chair, and it is my pleasure to moderate today's webinar. Next. It's CIFER mission to translate high-level research and knowledge to a diverse audience that includes policymakers, elected officials, and federal administrators. When we demonstrate the value of the profession to these groups, the Council increases public appreciation for research, extension, outreach, and academic programs in agricultural and applied economics. Before we get started, I would like to offer just a short introduction to the very important topic that we're going to discuss today. In this webinar, we will explore the critical role of agricultural R&D as a public good and the rising current concerns about funding trends. Public agricultural R&D yields exceptionally high returns, typically exceeding 10 to 1, through increased productivity and resource conservation, while contributing to economic growth, to environmental protection, and a safe, secure, and affordable food supply. Despite these benefits, in high-income countries, public agricultural R&D funding has waned, and in the United States, it has declined sharply, falling about 30% in real terms in the last several decades. Middle-income countries, on the other hand, like China, India, and Brazil, have surged ahead in both agricultural productivity and agricultural R&D. In this webinar, these three exceptional professionals, will examine how agricultural R&D functions as a slow magic with long time horizons for payoffs and will warn us that reduced investment has already begun to contribute to slowing productivity growth amid mounting pressures for climate change and rising global demand for food and bio-based energy. They will also discuss of emerging opportunities and emphasize the urgent need for renewed public investment in both basic and applied research to sustain U.S. competitiveness and support farmers as well as protect the ecosystem and ensure long-term food sustainability. Next. CIFER assembled these panel of experts, these three panelists, to discuss their work, starting with Julian Olsten, who is an agriculture economist known for his work on the economics of agriculture and food policy. He has a PhD in economics from North Carolina State University, and until 2022, served as a distinguished professor in the Department of Agriculture and Resource Economics at the University of California, Davis. Next. The next speaker is Iuris Lantz-Ballos, who is a research associate professor at the Center for Global Trade Analysis, GTAP, at Purdue University. Iuris's research interests are on food sustainability issues, the global farm food environment nexus, agricultural research investments and productivity, local global telecoupling, and computational economic modeling. He co-developed a simplified international model of agricultural prices, land use, and the environment, known as SIMPLE. Next. The third panelist is Dan Blaustein-Rito, who is a director of food and agriculture at the Breakthrough Institute, where he leads research and policy analysis on agricultural innovation and sustainability. His work focuses on how evidence-based policy can accelerate technologies that reduce agriculture's environmental footprint while supporting productivity, promoting resilience, and exploiting economic opportunity. Next, please. Before we start, I want to hand things over to our panelists. I'd like to remind you that you can submit questions for the speakers in the chat box at any point in time throughout the webinar. We'll hold the Q&A session at the end of the presentations, where our panelists will try to address all of your questions, either online or following the webinar. Next. With that, I would like to hand over the webinar to Julian. Julian, the floor is yours.
Thanks, Gal, and thank you and CFARE for organising this webinar on this very important subject. Next, I'm going to try in 10 minutes to cover a lot of ground here, talking about the slow magic of agricultural R&D, a phrase that we owe to Phil Pardey. The economic growth is driven by innovation, and agricultural science is crucially important to the sector. It takes a long time between investing in research and having consequences from that, and then they last a long time. Next, we have compelling evidence that there have been very high rates of return in the past to these investments, and no reason to expect that to be different in the future. Unfortunately, we've seen significant slowdowns and even cutbacks in spending on agricultural science around the world, not just in the high-income countries, but especially there. And this is happening at the same time where we're seeing a slowdown in productivity growth, and that's also pervasive next, not just in the high-income countries, but all around the world. So we have problems looking forward, thinking about the global food equation, the supply and demand balance, where we're going to anticipate substantial growth in demand for production from farms, attributable to income growth and population growth. But on the supply side, we have concerns because we have to deal with climate change. We won't have as much agricultural land to add and water as we've done in the past, and productivity growth is slowing. Next. So first to the slow magic. Next. This is a stylized picture of the time it takes and the research process, beginning with a period of perhaps 10 or 15 years spent investing in R&D, developing innovation as a result of that and technology. And then following that period, we have another 10 or 15 years during which those results are adopted on farms, giving rise to streams of benefits. And then eventually, this technology is replaced with some other technology, either because it becomes less effective or because better technologies arise. So we have this process where we incur costs over 10 or 20 years, and then we get benefits over the next 20 or 30 years. And so it's a long-term process. Next. And even though it takes such a long time, the benefits are large enough that they eventually are worth much more than the costs in the early period. So we've done many studies, hundreds of studies yielding thousands of estimates of rates of return. Next. These are internal rates of return. I want to talk about benefit cost ratios instead. And what these results show is that over these hundreds of studies and thousands of estimates, the average across all these studies is a benefit cost ratio of 27.9 to 1. That's fantastic. There's nothing else pays like this. And even allowing for the skewness of the distribution, the median across all these studies is 8 to 1. Next. If we look across these different high-income countries, the USA, other high-income countries, low-income countries, middle-income countries, the story is very similar. The mean is around 24, 25 to 1. The median is around 8 to 10 to 1. So this is pervasive evidence all around the world, hundreds of studies, and it's a fantastic rate of return. And there's no reason to expect it to be any less looking forward. Next. In addition to those benefits are based on measures of the value of productivity gains, which are eventually manifest as yield gains and cost savings for farmers, and then lower food and fuel and fiber prices for consumers. Next. But in addition to those, there are other benefits that are harder to measure and not included in these measures. And we have the value of increased resilience in the face of stresses from pests and diseases and climate. And we have the benefits from reductions in global poverty. We have less pressure on natural resource stocks, and we have less strife in the world when people are better off. Next. So now, in spite of all that really good news about how valuable agricultural science is, what we're seeing is cutbacks in spending next, and a slowdown in productivity growth. So this is a picture of spending over the last 40 years or so. This is work done by Phil Pardey in particular in a recent article in Nature. This was published last December. So since 1980, we've seen considerable growth from 38 billion in real terms to 110 billion by 2021 in total spending on agricultural agri-food R&D. But you'll see that most of that growth, in fact, was in the middle income countries, and the high income countries has been fairly flat. Next. And so you can see now that the high income countries are responsible for less than half the world's spending on agri-food R&D, and the middle income countries have taken over, in particular China. And there we have the dismal performance of the world's poorest countries, for which this will be most crucial in the decades ahead. Next. There's also been a swing towards the private sector, and this is not just in the high income countries, it's worldwide. Next. Now, the big concern in countries like the United States, and in the United States in particular, is that not only has spending stopped growing, it's actually fallen considerably. So since 2002, US spending on public agricultural agri-food R&D has fallen by roughly a third. And it did that fairly quickly in the first decade or so of this century, and has been flat in real terms since. Next. While that's been happening, we've seen a slowdown in productivity. So this is US productivity. The first column is growth rates of US farm output, and this is for a 100-year period from 1910 to 2007. And it was about 1.6% over that period. But there was a surge in the middle of the century. So it was a bit faster growth between 1950 and 1990, and considerably slower since then, and especially since 2000. And this output growth was mostly caused by productivity growth. So you can see the next column is multi-factor productivity growth. And in fact, in the middle period, productivity growth accounted for more than the total growth in output. Actually, total input use fell in agriculture. So we've seen this slowdown in productivity growth since 1990, reflected in slower output growth. And it's true whether we look at total factor productivity, measuring all the inputs, or partial factor productivity, measuring labor productivity and land productivity. So we can see a surge in labor productivity and land productivity in the middle period. But this is even faster growth in productivity, because what agricultural R&D was doing was enabling saving of land and labor. So land and labor productivity grew even faster than total or multi-factor productivity. Next. This picture shows a smooth series of multi-factor productivity growth over that period from 1940. And you can see the surge. It peaked in the around 1975 and fell down to about 1% or so in 1990, and it's been flat since. And then you can see that this slowdown in productivity happened while agricultural R&D spending was growing. And because of the long time lags, the slowdown in spending we've recently seen, and then the cutback in spending, we've not begun to see the effects of that on productivity. So the concern here is that productivity growth had already fallen and was low, and now we've cut back on spending. And in the next 10 or 20 years, we'll feel the effects of that. Next. So the trouble is we're going to have this, this is a global phenomenon, not just American. Next, we have this slowdown in supply growth and increasing demand growth. And the bad outcomes from that, people don't like high food prices. So we've had concern over high food prices during the pandemic. Looking ahead, if we have less productivity growth in the United States, we'll have higher food prices, we'll be less competitive internationally, farm profitability will be less, and the balance of trade will move against us. Looking around the world, we'll have more poverty, we'll have more stress on natural resource stocks, we'll have less climate resilience, and we'll have more strife in the world. Next. A recent study by Ariel Ortiz-Bobea and others estimated how much extra R&D would be needed just to balance the decline in US agricultural productivity that would be caused by climate change over the next 20 to 50 years. And what they estimated was that just to balance that and restore productivity growth that would happen if climate change hadn't happened would require an extra, would require R&D spending to grow from 2021 to 2050 at 5 to 7.8% per year, faster than it is now. And if you did that instead by a one-time increase in annual spending, you'd have to increase by $2 to $4 billion per year. Next slide. To put that in perspective, the United States is spending currently about $6 billion a year on agricultural agri-food R&D, which is less than $4 billion. It's rounding error in the total USDA budget of $214 billion for 2025. Last year, ad hoc assistance measures cost $42 billion in that year. So the scale of this is relatively small, and we're talking about having to double that amount simply to balance the effects of climate change over the next 20 years. And one way would be to do that would be by growing the spending by 5 to 7%. But remember, we have to wait 10 to 20 years before it takes effect. So I think incremental increases may be too little and maybe too late. And whatever harm happens will persist for decades to come. Thank you.
Thank you very much, Julian, for sharing these numbers with us. The next speaker will be Juris. Juris, the floor is yours.
Thank you, Gal. Can you, okay. So the presentation that I'm gonna show would be focused on the co-benefits from R&D-driven agricultural productivity growth. And some of these co-benefits were already discussed by Julian in terms of like reduction in input use and also in enhanced food security. Next slide, please. So we know that productivity gains would allow us to produce more by using less. So a good research question is how could we measure these gains? And in my work, we typically rely on economic models. So these are models of, let's say, agricultural sector or the whole economy. And we use these types of models to create scenario analysis. So essentially, we could simulate a scenario with this R&D-led productivity growth and without this R&D-led productivity growth. And from there, by taking the difference of the model outcomes, we'll be able to analyze like the co-benefits from pursuing such policies in terms of reduction in environmental impact of agriculture and also increased food security. So for the rest of the presentation, I will cover some of these examples. So first, I'll look into the historical experience, looking at the Green Revolution and how that historical increase in productivity have an effect in terms of reducing agriculture's environmental footprint. And then I'll discuss some of the feature work that we've done in terms of like increasing agricultural R&D investments in the US and globally. And then finally, I'll just touch base again on this issue of R&D investments and how we could use it to offset some of the climate change impacts. Next slide, please. So one of the biggest transformation in, I think, the 5 decades in terms of global agriculture would be the Green Revolution, wherein the developed regions as well as private institutions, they invested a lot in cultivating national and international agricultural research centers. And the main purpose of that is they wanted to have these centers develop, new agricultural practices and also improve crop varieties that could boost yields in the developing countries. And this is a work by Keith Fugly, one of my longtime collaborator. And essentially, they were able to estimate what are the productivity growth from adopting the modern crop varieties that these national and international research centers develop. And we could use these estimates in order to plug that into our economic models to see what are the co-benefits. Next slide, please. So again, the main intuition here is that when you don't have an increase in productivity, you'll have to increase resource use, and that would have a trickle-down effect in terms of your environmental outcomes. So, and then in our study here, we simulated the scenario with and without this adoption of modern crop varieties. And the key result is that we're seeing that with the historical adoption of improved crop varieties developed by these national and international research centers, we see that globally there's less land use expansion, there's less land use change GHG emissions, and more importantly, it has resulted in avoided extinction of threatened plant and animal species. And again, the key idea here is that if you have an increase in productivity, you'll have to use less resources. That means less land is going to be converted from natural use to agricultural use. And in a way, it indirectly preserves some of the natural habitat for threatened plant and animal species. Next slide, please. Now, in the literature, we could directly model the dollars spent in R&D and try to link that back into productivity growth. And this figure just shows you what are the historical productivity growth in agriculture, the red dash bar, compared to this modeled R&D-led productivity growth, the colored bars there that you see. And in general, you see that this type of framework is actually approximate the historical change in agricultural productivity growth that we've observed. So we could use this framework in order to do some projection scenarios. So in the next couple of slides, I'm going to show you some of these examples. Next slide, please. So this is with the work with Breakthrough Institute. And we were asking this question that, for the US, what would be the impact of doubling R&D spending from this period, 2025 to 2035? And what we found is that we could boost agricultural output in the US by around 20%. And it has little impact on US cropland use and also the agricultural GHG emissions. Now, the cool thing that we did in this paper is we could actually combine this increase in R&D spending with a more direct policy that limits farm input use so that we could further reduce agriculture's environmental footprint. Next slide, please. Now, here, this is more of it's another work, but it focused more of like globally what would happen if we increase agricultural R&D spending. And we simulated, again, two scenarios similar to the typical work that we do with economic models. One is the business as usual, and one is this increase in global R&D. And again, what we found is that increasing global R&D, that would lead into agricultural output growth, and it would also lower agriculture's GHG emissions from land use change and also farm gate emissions from both input and output. And more importantly, this global increase in R&D is critical for enhancing food security. And we were able to measure that through this metric of caloric undernutrition count. So this takes into account average changes in dietary consumption for different parts of the world. And again, if you increase global R&D, you'll see further reduction in the number of people who are currently experiencing caloric hunger. Next slide, please. Now, this is like a final example, and I think Julian already talked about this for the US case. But we can think of R&D as a way for us to, as a policy for us to offset the adverse impacts of climate change. And globally, we did it in the past. We did like a global scenario, and we were able to estimate that we need a substantial increase in R&D investment This is already 2020 to 2040. And in our estimate, we're seeing an increase of around 187 billion to close to around $1.3 trillion, the total investment that we need. And then for the US, you also need substantial investment. And this is from the most recent work by Ortiz Bubaya et al. But even though these are big numbers, we can make a stronger case for such investments by pointing out that, hey, if we invest in R&D, you'll have reduction in agriculture's environmental footprint. You'll have less cropland expansion, less land use change GHG emissions and agricultural emissions. And it would also lift people out of caloric hunger. Last slide, please, the conclusion slide. Yeah, just to conclude, R&D-driven productivity growth can enhance agricultural's output. At the same time, it could reduce agricultural's environmental footprint and enhance food security. And I would like to echo what Julian is saying, that we need agricultural investment, increase in agricultural investment now. And we could further justify these investments by pointing out these co-benefits. And then the last slide is just resources. Thank you.
Thank you very much, Iris. With that, we'll move to Dan from the Breakthrough Institute.
Thanks, Gal. Thank you, everyone. Dan Rayta, I'm the Director of Food and Agriculture at the Breakthrough Institute. And on the next slide, please. If you're unfamiliar with the Breakthrough Institute, we are a think tank that identifies and promotes technological solutions to environmental and human development challenges in a number of areas, including clean energy and also food and agriculture. And our work broadly is rooted in this philosophy that we've developed called eco-modernism, which is a pro-technology, pro-growth, and optimistic philosophy. My work here has spanned about 8 years or so, leading our R&D and innovation policy efforts, putting together reports on the environmental benefits of public US R&D funding, some of that in partnership with URIS, as he just mentioned. We've also tracked trends in R&D, including how much goes to different research areas like climate mitigation. And we've also published work going beyond R&D, looking at other policy mechanisms to drive economically beneficial and environmentally beneficial innovation, such as in financing and regulatory reform. Next slide, please. But I want to spend this presentation really digging into why we're seeing some of these declines that Julian and Juris talked about in funding, despite all of the benefits that R&D provides. And I think one overarching reason that frames much what I'll talk about is that there's been a real lack of support from farm groups. If you go to many commodity and farm groups and you ask them if they support R&D, as they've told me, they'll probably tell you, yes, of course we do. But on our list of top 10 requests for government, it's number 11. They support it, but they rarely prioritize it. So I'll talk about a couple of reasons why I think this is. Next slide. One is the productivity paradox, often referred to as Cochrane's treadmill in the economics literature, that when research and innovation leads to cost-cutting, productivity-enhancing technologies, the first early adopters, they benefit. They see their profitability increase because they're able to compete better with other producers. But as other farmers in the country also adopt that technology, which often happens quite rapidly in agriculture, as we've seen with improved seeds, supply increases and prices respond by falling because many agricultural goods are quite inelastic in demand. The development of new markets, both internationally, such as through increased exports, or domestically through developing new uses for farm goods, like for biofuel, can help offset this a little bit by increasing demand. But as you'll see on the next slide, the prices for most major commodities have significantly fallen as productivity has grown. This is great for consumers, as Julia mentioned. Consumers see quite large benefits, and some other stakeholders in the food supply chain do too. Food processors, livestock producers, they're able to purchase crops, some of their primary inputs, for less money, but farmers see the benefits of this R&D and productivity growth really eroded by this market response. Next slide, please. A second big barrier is the delayed benefits that you've heard about. This is a slide from one of Joris's papers. Across a wide range of papers, you'll see that typically the peak benefits for productivity growth from an investment in R&D happens roughly 20 years or so, give or take a few years after that funding investment. And that's just way beyond the timescale that most farmers and farm groups really find relevant. They're often focused on next year or even the current year and finding policy fixes for decreased prices, high input costs, etc. today. A prime example of this, as you see on the next slide, has been CRISPR, where the foundational research for it really was funded and occurred decades ago. Initially in the early 1990s, where scientists first discovered CRISPR, and then more famously, perhaps, in the early 2010s, when Jennifer Doudna's lab, funded by federal agencies, figured out how to use CRISPR to edit very precisely the genome of different organisms. Other researchers and companies, often with USDA support, have taken that and applied it to develop an amazing range of different gene-edited crops, some to have higher yields or to be more nutritious, to reduce food waste, or to combat important pests like citrus greening. And we're seeing many of these go through the regulatory process now, but still, decades after this initial infusion of federal foundational R&D, we still see almost no acres being planted with gene-edited crops. I believe we will soon, but regardless, this really illustrates how incredibly important and beneficial and revolutionary technology has still taken so long to bear fruit. Next slide, please. A third barrier is that the actual focus of R&D has shifted, often away from farmers, away from many of the topics that benefit them and that they care about most. For example, the share of state agricultural experiment station spending has shifted from being around 2/3 focused on farmer productivity in the 1970s to only about half of it being focused on it today. The rest is focused on other important topics, nutrition, environmental stewardship, for instance, but these really indirectly affect farmers, if at all. Next slide, please. Lastly, there are often diffuse benefits from public support and public funding for R&D. For instance, in the early 2000s, citrus greening was first discovered in Florida. And in response, USDA and Congress invested hundreds of millions of dollars in research to help combat it and prevent it. But it didn't pan out. Florida's industry still lost billions of dollars in revenue. And instead what happened is California, where citrus greening was slower to arrive, they were able to learn from Florida's experience and much of that research and better protect their industry, such that although they've still been hit to some degree, they've thrived relative to Florida. Now, this type of positive spillover effect or technological overflow is great from an abstract perspective. It increases the benefits of R&D. We want to see other states, other countries learn from and build upon research that happens across the country. But it really does create a political hurdle or the local R&D, though it sometimes has local benefits, perhaps as often as not does not. Next slide, please. Next slide. So, oh, please go back one. There are a number of solutions, I believe, to increasing political support for R&D. I'll just touch on 2 or 3 of them, really. So one, just going beyond farmers for a second, I think we need to recognize that R&D does, as Julian mentioned and Iris mentioned, have benefits for a wide range of stakeholders outside of farming. There's a really strong case, I believe, for consumer groups, for the food industry, environmental groups to come together to support R&D funding. 2, as you see here on the slide, there are many opportunities to make R&D work better for farmers. Prime mechanism for this is through public-private partnerships, such as what the Foundation for Food and Agriculture Research, or FAR, does, as well as the fund more regionally and locally tailored R&D. But as you see on the next slide, any shift in funding to better support more farmer-responsive research still needs to protect the base or foundation of applied research. It can't come at the expense of funding for NSF, for foundational research through USDA's Agricultural Research Service or other sources, because the breakthroughs of 2050, the CRISPR of 2050, if you will, really starts with that base of support. Thank you for your time.
Thank you very much, Dan.